And soft soil means a very slow shear wave velocity. You have something very smooth, so the propagation is very low. So after the penetration of the incidence of wave in the soft layer, as I said before, they are going to be trapped due to the interface between the bedrock and the soft formation. And imagine that you have a certain height of soft soil, and as soon as you have a body, you are going to have a resonance frequency. So here you have a column of soft soil with a certain height, with a certain stiffness, and this configuration is going to be relative to a resonance frequency. And if the frequency contained of the earthquake is very energetic in the frequency band that is not far from the resonance frequency of your soil column, you are going to have a resonance phenomena. So you are going to amplify the response. And in fact, as I say, not directly, but the fundamental frequency of the soil layer, when I speak about fundamental or resonance frequency, it means when there is an elastic behavior of the soil. So the fundamental frequency of the soil layer is linked to the stiffness of the soil, so the shear modulus of the soil, and the height of the soil column. So as a result, when we look at the earthquake, the most important part of the earthquake is the frequency band that corresponds to the low frequency, because most of the time this is these frequencies that are going to induce very high damage to the buildings. So as I say, if you have a soft soil with a very high with a layer with a very thick layer, in this case this layer of soil is going to amplify the low frequency. So if you have very tall buildings that are built on this soil column, you can have a phenomena of resonance between the soil column and the building, and a lot of damage. At the contrary, if you have a stiffer layer with a small thickness, in this case, this configuration is going to amplify the frequency that are a little bit higher. So in this case, if it can correspond to the resonance frequency of a small building, so you can have damage to the small building for this configuration. So here below, this is an example of the Mexico City. So in Mexico City, you have a sedimentary basin with a very thick layer of very smooth clay. So in this configuration, the clay layer amplifies the frequency around 2 hertz. 2 seconds, sorry, for a period of 2 seconds, so 0.5 hertz, so it's very low for earthquake. And here you are in a gray brown, let's say like that. You have the acceleration versus the period of what has been recorded at the outcrop on the bedrock, okay? And in a red, you have the frequency contained in terms of period here of what has been recorded at the soil surface in the sedimentary basin, and you can see that there is a very large amplification of the 2 hertz building, and this is what we can see here. These 2 buildings have finally a frequency that is not far from 2 hertz, and they have been completely destroyed, and it was not the case of this other one. So now just speaking about the scale that we are interested in when we work in geotechnical earthquake engineering. So for a seismologist, what is important is to see what are the site effects. So it's at the scale of the sedimentary basin of the mountain. This is at a regional scale. But when you are geotechnical engineer, you are interested about by a smaller scale. This is the scale of the building and the soil column below the building. And if we have a look to the Eurocodes, for instance, we have to know the property of the soil column for the first 30 meters. Okay. But if we look, we have also the problem that emerged since several decades is in addition to the soil structure interaction, one building, one soil column, you have soil structure interaction in the case of the town. Because if you have two buildings with almost the same frequency and that are built on the soil, if one building is going to start to vibrate, let's say at 1 Hertz, so it's going to have to create inertial loading due to its mass and its acceleration. So you are going to have, due to soil interaction, you are going to have transmission of this inertial energy, one part, to the soil, and is going to be transmitted to the neighborhood building, and if it has the same frequency, it's going to amplify. So this is what we call soil structure interaction. So this is at the level of the town, but it's very complicated task to analyze that. So it means that when we're in geotechnical earthquake engineering, is that interface between three domain: the seismology, the geomechanics for soil behavior, and the dynamic of the structure, as soon as we speak about soil structure interaction. So as I said, we are not interested by the source of the earthquake, but we're interested by the building and the first 30 meters. And in the Eurocode, they say that when you start a study, first you have to know the geological, you should have the geological and the hydrogeological description of the site. You should know the property of the soil column for the first 30 meters, and you should know the solicitation that we have at the bedrock or at the soil surface. So here, this is a drawing that summarizes what we should look after when we start a study. So you have a soil column with the bedrock. So here, this is a very simple soil column. So first, you must know the geology. So that means the stratigraphy and the kind of soil that you have, clay soil, sand, and so on. You should also know where is the level of the water table, because you have to be careful. If you have, for instance, loose sand that are saturated, so that are below the water table, and most of the time less deeper than 50 meters, you can have a risk of liquefaction. That is a main problem in geotechnical earthquake engineering. So if you want to build a building, you have to think about remediation. So it means that you should have geomechanical data. You should know what we call the cyclic resistance, okay, for this loose sand that is saturated. This is the first part. And the second part is you have to speak with seismologists, because you have to know the solicitation that can happen in this area. So you can have the free field acceleration, which is this acceleration at the surface, or you can have by deconvolution process. This is a processing of the data from the surface. You can obtain the acceleration at the base of the surface of the bedrock. Okay, so you need that, and after you are going to look at the soil structure interaction, because due to the presence of the building, so it means due to its mass and its stiffness, the movement of the soil at the level of the foundation of the building is going to be different from the movement at the same level but in the free field. Because due to the mass acceleration mean inertial interaction, and stiffness of the foundation, but is of course different from the stiffness of the soil, mean that the waves that are going to hit the interface between the foundation of the soil are going to be reflected. So you are going to change the acceleration, but we will see that after. So when you are in a seismic area, you have to follow the regulations. They impose seismic rules for new construction, and actually this is the Euro Code 8.5. So this document asks you to analyze if there is a risk of liquefaction. It gives some advice to design different system of foundation, so shallow foundation, mixed foundation, deep foundation. It also gives some advice for the design of earth retaining structure, and there is a chapter devoted to soil structure interaction under seismic loading, and it helps the engineer to know if it should take into account the soil structure interaction. So one part that is called the inertial effect, and the other part that is called the kinematic effect. So as I told you, we have to take into account the first 30 meters of the soil column. And the first parameter is the shear wave velocity, Vs, that is linked to the shear modulus and the density of the soil through this equation. So here, sorry, it's in French, this is the table that is provided in the Eurocode. So here you have, so the parameter, so it is recommended to have this data, so the Vs value. So you can see that the type of soil A, B, C, D, and so on are classified depending on the value of the Vs. If we do not have directly this data, we can use some result of a SPT test, standard penetration test, or of CPT test, standard penetration test, or we can use for clay soil the value of the undrained shear strength, the undrained cohesion. But for instance, the SPT, there exists some correlation to obtain the value of Vs, but for certain kind of soil. But it is recommended to focus first on the shear wave velocity. So this is the generalities for this part. Now we are going to switch to soil dynamic and cyclic strain property of the soil. So here, this is a simplified representation of what happens when you have an earthquake. So the thing is that as a first approach, of course, an earthquake is going to create shear wave and P waves that propagate in different directions from the sources. But most of the times, what we have is that we have a stratigraphy with an increasing stiffness with depth. So, and when body waves or shear waves in this case propagate from a stiff layer to a smoother one, you have, due to the Snell law, for instance, if you start to propagate in this direction, if you have a stiff layer and a smoother one, the direction of propagation is going successively to be oriented in the vertical direction. So as a first assumption, and because of the shear waves as the most dangerous waves for building, we assume that the earthquake is can be represented by a vertical propagation of shear waves. Okay, so here this is on your, for you it's the left hand side. On the left hand side you have an initial element of soil at rest. So you have the vertical loading due to the overlying layers, and of course you have the horizontal loading due to the presence of the soil on each side. So you have the state of stress at rest. Okay, imagine that you have and here this is a molecular representation of the state of stress at rest. Imagine now you have a vertical propagation of shear waves, so it's going to create shear waves on the horizontal plane, and due to the presence of the soil on each side, you have what we call complementary shear strain. Because if you can imagine, if you do not have that, the soil element is going to rotate. So if we work with the Moore-Coulomb cycle, so the initial state is this state. So from the surface that are at initially with an horizontal with sigma h and sigma v, you have the application of the shear waves, so they become this state of stress for each side, horizontal and vertical. Let's take the example of the horizontal one. So this is state of stress. So if you create a plan which direction is the direction of the surface, you hit this the circle here. You do the same thing for the horizontal plane. Imagine you do not take into account this very small inclination. So here we have what we call the pole. Okay, and after that, so you can have here, if you join this point to the point of the principal vertical stress sigma 1, so you have the principal stress direction that is perpendicular to this plane. Okay, now we return at rest, and after that there is a shearing in the other direction, so you make exactly the same construction with the Moore-Coulomb cycle. So you can see that when you have a shear wave that propagates, you have a continuous rotation of the principal stress, sigma 1. Okay, so on another kind of representation, if we represent this stress path in the P', so the mean effective stress, which that is given here, with the deviatoric stress, this is the stress path followed by a soil element when it is subjected to a vertical propagation of shear waves. Okay. So here you have the element. So when you shear, you obtain a deformation that is called distortion, and the distortion is the ratio between the horizontal displacement over the depth, the height, of the soil element. So normally we represent the strain stress path in the distortion, in the shear stress versus distortion. So initially the soil is linear, but as you can see, the domain of linearity of the soil is very, very reduced. So very quickly you start to have non-linearity. This is, you can see that with the curvature of the stress path. And after that, so this is the first direction of loading. There is an inversion of the shearing. Okay, so here you have the plastic deformation. and after that you go up. Imagine that is stays control in strain. You reach the maximum deviatory strain, the maximum shearing strain here, and you reload the soil element. So you have its form a loops, so it's characteristic of an hysteretic behavior. Okay. And of course, if you have a static loading without any cycle, you can obtain this curve. Okay, and this curve is what we call the backbone curves. And here, of course, we reach the maximum shearing resistance of the soil element. So, when we have a loop, stress path that describes a loop, the inclination of these loops characterize the stiffness of the soil. So there is different parameters. There is what we call the G max, the maximum shear modulus. Normally, these values you obtain, for instance, inside with a geophysical test, and it's concerned the value of 10 to minus 6 up to 10 to minus 5 for the distortion, so very small distortion. And as soon as you continue to shearing, you have a curvature. So on the curvature, you can select one point, and you have the tangential shear modulus, that is the instantaneous modulus at time t. Okay, and after that, you can also characterize the average stiffness of the soil during all the loops, so on the range of strain distortion concerned, by what we call the second shear modulus. Okay, and here, yes, for the reference shear strain, but no, I don't use it, but the reference shear strains, in fact, this is the shear strain that we have that correspond to the shear strain of the slope of the line G max that cross the value of T max. So in this case, it should be around here. But it's used in some empirical expression of G max. Okay, and after that, so as you have a loops, it's mean that you have hysteretic damping. Okay, the origin of hysteretic damping is a plastic one. So when you have loops of loading, you are going to create plastic deformation. So the particles of the soil are going to change in position, and you need energy for that. So this is a consummation of energy. So this is why you have damping. Okay. So there is a definition of the hysteretic damping. In fact, this is the ratio between the surface of the loop and the triangle that is in the hatch area on the drawing. So here, this is the expression of the material damping that is useful. So this is two representations that are very used in geotechnical earthquake engineering. So the thing is that so the soil is defined by the shear stiffness through the shear modulus, and also with the damping ratio. This is the material damping. And what we see experimentally is that these two parameters are very sensitive to the level of the shear strain. Okay. Here, this is an example. On your left-hand side, you can see that when you increase the level of the shear strains, the inclination of the loops is through the direction of the is going to decrease. And what we used to do is to represent the evolution of the value of G versus the distortion. So we start from G max with a distortion that is very, very small. And you can see that there is a decrease of the value of G versus the distortion. After that, you have the damping ratio. And here, at contrary, as the soil become smoother when we increase the level of the shear strain, the damping of the soil is going to increase. So this is what we see on these curves. And most of the time is represented versus the logarithm of the shear strain. Now, another parameter that is important. So to explain this one, we start from theoretical assembly of elastic sphere, on the which one is applied the stress at rest, and we start to shear this assembly of elastic sphere. So when the shear forces is lower than the shear resistance that comes from the contact between the sphere, you have only a very, very small sliding at the scale of the contact. But as soon as that the shear stress is equal to the shear resistance, you are going to have a large sliding, important sliding, and the particle is going to move, and you are going to have a reorientation of the grain with an evolution of the volumes if you are in drain condition, or at counterpart, if you are in undrained condition, you are going to have an increase of the pore pressure that corresponds to the drain case to a decrease of the volumes. So this we characterize so the time at which we start to have an evolution of the volume, or the time at which we start to have an evolution of the pore pressure in undrained condition to a certain level of the shear strain, and we call this parameter the volumetric threshold shear strain. So this is the value of the shear strength above which we start to have volumetric deformation, or in drain case or in undrained case, pore pressure generation. So here this is the expression that we can have from a geometrical approach. But what we can find if we consider that these elastic spheres are made of quartz, and we consider an isotropic stress between 25 and 300 kPa, we found that this volumetric threshold shear strength is between 10 to minus 4 up to 6 times 10 to minus 4. And finally, this is not very far from what we can observe on sand, but almost made of quartz, of course. So here, this is some experimental curves that has been obtained on the left-hand side for sand, and on the right one for clay or argillaceous soils. So for sand, this is the pore pressure built up that is represented versus the amplitude, we are in strain control test, versus the amplitude of the cyclic shear strain that is applied on the specimen. So you can see up to 10 minus 2%, so 10 to minus 2%, so 10 to minus 4, we do not have any pore pressure increase, pore pressure built up inside the sand. But as soon as we reach this value, we start to measure pore pressure built up inside the sample. Okay? And in the clay domain, this value is larger, and we can, here it is represented also the vertical shear strain versus the cyclic shear strain amplitude, and we can see that we start to have deformation. This one is related to volumetric deformation. We start to have volumetric deformation, but for a higher value of shear strain. Okay? And this is due to the fact that this value of shear strains is linked to the, let's say, a little bit the connectivity of and the arrangement of the grain inside the soil, of course. So if we summarize, we obtain this kind of figure. So here, normally what we do if we do not represent the value of G versus the shear strain, but the ratio between the value of the shear modulus over the maximum value of the shear modulus. So we have, this is this curve that is represented versus the shearing amplitude, but at the with a scale in a logarithm, and you have here the damping ratio curves. So we have first, so the elastic limit. So when this on this side, on the left hand side of this limit, we do not have any plastic deformation. So you see that you have almost no variation of the damping at a very, very small value. And the value of G is more or less equal to the value of G max. As soon as you start to have plastic deformation, you start to have an increase of the damping and the decrease of the shear shear modulus. So here you go from a very small strain, a linear behavior, and you start to have not so very small but small strain with limited non-linear deformation. And here you have no degradation, so you can apply a lot of cycle of loading, and the soil won't be degraded. And after that, you reach the volumetric threshold shear strain, and you have an increase of the slope, so you start to degrade very rapidly the shear modulus and to increase very rapidly the damping, and you start to have medium to large shear strain. And here you have creation, if you are in saturated case, you start to have creation of pore pressure, and if you are in undrained condition or in dry sand, for instance, you have a volumetric deformation, you have a densification. In this case, you have a degradable behavior. So it means that if you apply a series of cycles in strain control test, you start to have, with the number of cycles, the stiffness, the average stiffness of the soil that is going to decrease for the same level of cyclic strain loading. Okay. So there is the first parameter, the main parameter that influence the shear strain and the damping ratio is the shear modulus and the damping ratio is the shear strain, so that's the main one. And after that, you have also the plasticity index, because the nonlinear behavior of the soil is linked to the connection between the particles of the soil. So when you have a sand, a pure sand, the number of connections is lower than if you have a clay or a mixture between sand and clay, where the clay is the main matrix. So the behavior is controlled by the clay. And in this case, so you have more easily plastic deformation when the connections are not so high than when the connections are high. This is why it is represented here versus the plasticity index. The shear strain threshold for elastic to plastic deformation, and the volumetric threshold versus the plasticity index. So you see here 0, you are in the case of a pure sand, and here so you increase. So you can see that these two parameters are translated on the right hand side, so on the side of higher limits. So it's modify the shape of the what we call the degradation curves, that are these curves. Yes, I forgot to say that. So these two curves are called the degradation curves. Okay. So we have seen that there is the effect of the strain, shear strain level, the main one, and another one is the plastic index, and a third one is the initial state of stress. So the initial state of stress has almost no effect when you have a very plastic soil. This is what is illustrated here. You see that this curve corresponds to the degradation curve that has been obtained for different level of initial mean effective stress. So for 1 kilonewton per square meter cubics, up to 400. So you see that there is no lot of difference. But when you have a sand, there is a high difference. It means when you increase the stress level, the range of shear strain for the which one you have an elastic behavior is enlarged. We can see that here. It's enlarged a lot. So you have a translation of the degradation from the left to the right when you increase the shear stress, the initial state of stress inside the soil. And finally, the fourth parameter that can influence the behavior is, I have ever spoke about that, is the number of cycles. As I repeat that when the level of the shear strain is higher than the volumetric threshold, if you have a lot of cycle, you have you start to have degradation of the property of the soil. So you start to decrease the inclination of the loops that go to the horizontal, in the direction of the horizontal. So you have this effect. So just to tell you the difference between what is actually applied inside in the Eurocode, they do not speak about the number of cycles of loading. It's not taken into account. And it's to say that an earthquake most of the time is less than 10 cycles, equivalent cycle. So I present you quickly so the two main parameters are shear modulus and damping ratio, and their evolution with first the shear strain and the 3 other parameters that can have an influence on the degradation curves, but how these parameters are determined, such as, for instance, they can be determined, for instance, from shear wave velocity, as the value of the shear modulus is linked to the shear wave velocity through the density of the soil. So there is an in-situ test. So at low level, you have all the tests that are performed in geophysical approach, with a geophysical approach. I will just give some detail on seismorefraction and cross-hole, down-hole and up-hole test. And you have on the other side more geotechnical tests that induce a large deformation in the soil. but you can obtain the value of the shear wave velocity or the Gmax that correspond to low level of shear strain through correlation. So there is the SPT, standard penetration test, the CPT, cone penetration test, and also the lactometer, pressure meter. On the other side of in situ, there is the lab test. So there is two main categories. So the first one concerns the low strain level. So you can obtain, for instance, the BMAX 3 if you have, for instance, a triaxial test that is equipped with Bender element, or you can do a test with a resonant column test. And on the other side, so it's unable to determine the first part of the degradation curves. And on the other side, you have large level distortion tests. So it concerns the triaxial test, the simple cyclic shear test, cyclic torsion test. And it concerns the lower part, the last part of the degradation curves. So to obtain the total degradation curves, we need to perform low and large level tests. And after that we have, but it's an exotic one, the model test. In fact, with the centrifuge and the embarked earthquake simulator, the shaker, we can obtain so the degradation curves through only accelerometric measurement. I will explain later. So first with the in situ test. So here this is seismic reflection test. So you have an transmitter at the surface, and you have a series of a receiver, and you are going to hit the transmitter, and it's going here. This is an example of a two-layer substratum with horizontal stratification, because this kind of test can be used for horizontal up to several degrees of inclination for the stratification, and it should also be used only if you have an increase of stiffness with depth between the layer. So here you have the shoot, and you have the direct waves, okay, and here you have the waves that are going to hit the interface, and you have the refracted waves. With a critical angle of incidence, you have an horizontal propagation of the refracted waves that are going to be refracted in the first layer at each time. So this is the head waves coming from the refracted waves, and you have some receiver, and you have here, for instance, a critical distance x index c. For the which one the time request for the surface layer, the direct wave, to reach this point, and the time request for the indirect layer to reach this point are the same. Okay. So and from the identification of this point, we can obtain the value of the Vs of each layer and the height of each layer. So this is a characterization to obtain the VS40 from that is needed from the Eurocode. So this is a geometrical representation of a layer with the propagation of the waves. So you have the source, the emitter S, and the receiver R. So you have a wave that's going to hit the surface with a critical angle. From the Snell law, with this critical angle, you have an horizontal propagation of the refracted waves in the second layer with a shear wave velocity Vs2 that is going, and this wave is going to be refracted at each time with a critical angle, and at one time it will hit the receiver. So here this is only a mathematical expression of this geometrical representation. If you use the Snell law and the trigonometric relation that are written down, you can obtain an expression of the time at which the wave is going to reach the time after which the waves is going to hit the receiver, and at this critical distance, so you have the same times for the direct wave and for the indirect waves. And from, you can see here this is a constant, and here finally you have this is some kind of slope in the, if you represent the time versus the distance, so you will have this kind of things, and here you have 1 over V1, 1 over V2, and so on. So you can determine, because you have several receivers, you can determine these two values, V1 and V2, and with this equation you can obtain the height of each layer. So this is, no, I made a mistake, this is the arrival time and the distance here. This is the figure that we can obtain from the receiver, so you can identify the different segments of this representation to obtain the different value of the shear wave velocity, and from the expression of this expression for a multi-layer case, you can obtain the height of each layer. Like that, you can obtain the DS30, that is asked by the Eurocode. You have another test that is a cross-hole test. So the advantage of this test compared to the seismic refraction is you have 2 holes, or 1 hole for the emitter and several holes normally for the receiver, and you have sources, and you are going to hit and some receptor, and you can by changing the depth of the transmitter and the receiver, you can measure the shear wave velocity at different depths. The advantage of these techniques compared to the other one, to the first one, is that these techniques enable to detect a layer with a lower geomechanical properties, because in the first case it only enables you to detect layer with an increasing stiffness with depth. So this is most of the time we prefer this when it's possible, because it's more expensive. We prefer to perform this kind of geophysical test. And what we use, because the problem here, when you hit, you have most of the time creation of P waves and S waves that superimpose, and the P waves is faster than the velocity of the P waves is faster than that of the S waves. So what we use most of the time is we hit the emitter, we hit in one direction to create S waves, but we always have P waves, and we hit for the second test in the other direction, because the P waves is not sensitive to the direction of loading, but P waves is. So by this way, here you have the arrival P waves, and here, because the inversion of the loading direction, we can identify more easily the time of arrival for the S waves. So you also have what we call downhole or uphole. So uphole test is when you have the transmitter in the Brouwer hole and you have the receiver at the top, and downhole is when you have the emitter at the surface and transmitter at the bottom. So this test also enables to obtain the shear wave velocity profile as it is illustrated here, but I'm not going far away in this explanation. And after that, as I told you, you have the CPT and the SPT. So for the SPT, I think all of you know that. So it's the number of blow that we need to obtain an insertion of about 30 centimeters into the soil. So this test, for this test, we have a lot of correction that should be applied. So this, for instance, the weight of the hammer, the energy of the hammer, the effect of the vertical stress induced by the overlying layer and so on. And this test is most of the time very sensitive to the man or the woman that is going to perform this test. And after that, you have a CPT test that enable to obtain a continuous profile of the resistance at the tip of the CPT and also at the shaft. So you have the two values. And these two parameters, of course, are related to very high level of distortion with plastic deformation, but some correlation has been published in the literature that linked this value to the value of Gmax. But we should be careful with that because these correlations are relative to a certain kind of soil, in a certain region, to a certain age of this soil, and so on. After that, you have lab test. So one of the most used lab tests, but also very expensive to obtain the parameter for a low level of shear strain, is the resonant column test. So for this test, so you have a sample, so it can be cylindrical sample or hollow cylinder samples that are put in the resonance column test, and you are going to apply an harmonic loading. So it can be a torsional one or an axial one. So here, this is an illustration of the resonant column test that we have at the University Gustave Eiffel, but in Paris, Bar-la-Vallée. So you have the base of the resonant column test, and here this is the step of the creation of the samples. So here this is a case of a sand raining. Once the sample is created, we put some pieces at the top here because this is a drain test. And after that, we put the systems of loading because we are going to apply a torque, in this case, at the top of the sample. So the principle of the determination of the Gmax with a resonance column test. So in fact, imagine that we have so we are going to apply on the sample here. Imagine it's fixed. We are going to apply on the sample a torque. So here we have a torque, and here you have the value plus the variation of the torque versus, so you have the variation in this small element of the sample, you have the variation of the torque that is applied, and applying the equation of dynamic equilibrium, because you have inertia here, because of the velocity of the displacement is sufficient to create inertial forces. So the inertial forces are provided by this expression. So you have the density of the soil and the second polar moment of inertia, G, times the angular acceleration. So here we introduce the relation between the torque that is applied to the force that is applied, and we introduce that in the equation of dynamic equilibrium. So we can find this differential equation, and one of the solutions is provided by that, assuming that we are going to apply an harmonic loading, and the response, the distortion is going to follow also an harmonic evolution. So we have this kind of expression, and the constant C1, C2, D1, and D2 are defined by the boundary condition. Okay, So the boundary condition for the resonant column test at the base, we are in a fixed condition. So with this condition, we find that the first constant is equal to 0. After, you have the continuity of the forces and the displacement between the loading system and the top of the sample. So it means that the inertial torque applied at by the loading system on the top of the sample is given by that. You have the equality of the torque at the top, so you have this equality. And at the resonance, because we are going to reach the resonance at what time, we obtain this equation from the first one on the previous slide. And knowing that the frequency that corresponds to the maximal answer that we can obtain is verify this relation we can obtain by this way the shear wave velocity, so the value of Gmax. Because when you start to just an illustration to better understand, when we make a resonant column test to obtain under a certain state of stress and a certain level of shear strain, to obtain the value of Vs that correspond to Gmax due to the low level of shear strains, we are going to apply different loading with a fixed amplitude of the loading. So this is what is illustrated here. And we are going to obtain a certain magnitude of the displacement that is here. So we are going to select several frequencies and we can obtain the maximum amplitude of deformation that you are going to have. And all the time we can identify a peak, and this peak is due to the fact that we have a resonance frequency between the element that has a resonance frequency and the frequency applied. And by this way we can obtain the value of this frequency and thus the value of the Vs. Concerning the damping ratio, what we used to do is to analyze, to obtain the frequency, the damping ratio through free vibration. So we load the samples and after that we stop and it starts to vibrate freely, and we can see that we have a decrease of the response. And by analyzing the level of decrease between, for instance, this cycle and this one, we can obtain what we call the decrement, the logarithmic decrement. Here at the top you have the expression, and by this way you can obtain the damping ratio that is linked to the logarithmic decrement with this equation. So for the larger shear strains, we use the triaxial test. So I think everyone knows the triaxial stress. The thing here, this is a triaxial cell from the École Nationale des Ponts et Chaussées in Paris. So here I put the same representation as for a soil element when subjected to a vertical propagation of shear waves. And here, if we take once again into account the Morcoulon representation, we can find that compared to the loading applied by a vertical propagation of shear wave that created, I remind you, a continuous rotation of the principal stress axis. The principal stress, there is a continuous rotation. In the case of a triaxial test, of course, we have a rotation of 90 degrees, and you do not have a continuous rotation of the principal axis. But anyway, for instance, in the case of liquefaction study, to determine the cyclic resistance curves of the soil, most of the time we use cyclic triaxial test, and we consider that even if we do not have exactly the same stress path, we can use this result to analyze if there is some possibility of liquefaction in a loose sand layer, for instance. Here, just to illustrate the difference of stress path. Here, this is the stress path followed when a soil is subjected to a vertical propagation of shear waves with different initial shear stress of test. And here you have what you obtain for stress path in a triaxial cell. So you see that you have a difference, but we do not take into account this difference in the analysis. So once you make, if you do not make the test for liquefaction, but to obtain the shear modulus and the damping, so from the triaxial test you can easily obtain the Young modulus. After that you have a relation between the Young modulus and the shear modulus with the Poisson coefficient. So we can obtain the shear modulus. And concerning the damping ratio, we can obtain it by looking the phase lag between the application of the loading and the deformation, because this is an hysteretic behavior, so you do not have this, you should normally see, even if it's not very easy, you should see a phase lag between the maximum shear modulus and the maximum shear strain. So after that, we can also determine this parameter in centrifuge. So the Gmax can be determined by what we call Bender element. Bender elements are piezoelectric pieces. The principle is that you apply the tension to the Bender element and it's going to vibrate. So you have one emitter, one receiver, and the tip of the Bender element are separated by a certain distance. So when you apply tension, so it's going to vibrate, you are going to transmit the vibration through the soil, and it's going to hit the other Bender element that will start to vibrate, and these vibrations are going to create tension. So you can have, by recording the signal, we can have the time, and as we know the distance, we can obtain the shear wave velocity. To work well, it is recommended to have a certain distance between the two tips, between 1 and 5 centimeters, due to the level of the shear wave that are measured, because we should have between 1 and 2 wavelength of distance between the emitter and transmitter. So if this is some illustration, in our case we have this kind of Bender element here. And as I told you, we can determine, so with Bender element we only have Gmax, this is the only thing that we can have. And I told you that in centrifuge we can also obtain the degradation curve by using only accelerometer. So there is two kind of tests. The first one that we not use here is with a hammer, a hair hammer that we can put at the bottom of a container. So here you have a cross section of a container with a hair hammer and a vertical array of horizontal accelerometer, and by recording the acceleration, so we can by, for instance, at this level, okay, by considering the mass of a layer of sand that corresponds to one accelerometer, multiplying the acceleration with the mass, we can have the inertial loading. So we can have the inertial loading of all the layer, the inertial loading applied by all the layer on this level. So you will have the shear stress, sorry. And after that, by double integrating the accelerometer, you can have the displacement, so you can obtain the distortion that you have between two levels of acceleration. Like that, you can obtain the loops between distortion and shear strain. So you can obtain the degradation curves because you have the shear modulus and the damping. So this is what has been done, for instance, this is an example of test that has been performed here. It was in Fontaine-Lausanne, dense and dry. So this is the kind of loop that we can obtain. Of course, there has been a little bit filtered, and this is the degradation curve that that has been obtained because we have applied different level of input. So we have different level of shear strain. After that, so if we want to summarize for the test in lab, so you have for a very small level, so you have the resonant column or the bender element for Gmax. If you are going at higher level of shear strength, you are going to triaxial cyclic triaxial test. You can also use a simple shear test or torsional shear test. In the case of if we look relatively to the seismic movement, the seismic loading, we can go from almost all the range of distortion. But if we concern vibratory machine, we are more in the low level of distortion, and of course with explosion in the very high level. So the problem is that the lab tests are very expensive, and the other problem from in situ tests is of course you perform with geophysical tests, you perform tests on undisturbed sample, even if there is some skin problem in the borehole, for instance, but you cannot actually determine the damping ratio from the in situ test. This is not possible, so you need to have laboratory tests, but they are very expensive, and the other problem of laboratory tests is sometimes the sample has been disturbed. So are they representative of the true values? So if you do not have any money, you can also use some empirical expression of the degradation curve, that is to say from G over G max versus the strain level, and beta over beta max versus the strain level. So here this is some expression. Okay, so you can notice that of course there is the effect of the strain level, but there is also the effect of the plasticity index, as we have seen before. You also have the effect of the average effective state of stress. We have seen that, and you can see that there is no the effect of the number of loading is not included in this kind of expression. So this is some solution that you have for a first estimation, and after that you have the expression of the damping ratio that depend on the ratio between G over G max. So that depend also on the level of distortion, on the plasticity index, and on the level of the average effective state of stress. Now, if we look a little bit on the Eurocode side, first, concerning the characteristic of stiffness and damping, what the Eurocode say is that due to the influence of the shear modulus on the design seismic action, it should be taken in, this is the first parameter that should be taken into account, and they give the relationships between the shear modulus, the density of the soil, and the shear velocity, knowing that the shear velocity normally you should know it from the analysis of the soil column. Now it indicates also what the Eurocode indicates is that we should take into account the dependence of the shear modulus versus the level of soil deformation. So it's mean versus the shear strain. And for that, he gives some value in the cited paragraph. It indicates also that if we take in certain conditions, if we take into account the soil structure interaction, the damping ratio should be taken into account, but in some case it is neglected. And it indicates also that we should be careful that there is two kinds of damping. So there is the material damping coming from the analysis, for instance, of the hysteretic loops. So this damping comes from plastic deformation, and there is also what we call the radiative damping. So the radiative damping is a geometrical one. So you imagine that you have the surface. For instance, you have a sources which apply an harmonic loading, and here you have propagation of shear waves. So here the energy is completely concentrated, but here you can imagine that the energy per square meter of surface, for instance, decrease with the distance from the sources. So this is what we call the radiation damping. You have natural damping due to the propagation of the wave far away. So, if we continue in the Eurocode, as I said, if you are in stable condition, it means that there is no slope, there is no liquefaction or things like that. If you are in stable condition, so it indicates the shear wave velocity is the main parameter, it's the most reliable parameter, so you should use it, except if you cannot, if you do not have the data and you do not have the money for that. They also say that in critical case, that is to say for large structure, just a hospital, nuclear power plant for instance, and in area of high seismicity, in this case, the shear wave profile should be obtained from Borehole approach. So I remind you that seismic refraction, you cannot identify low property, a layer with a low property of low geomechanical property, but you can with geophysical method based on Borehole analysis, just like cross-hole test. If in other case, so less critical case, if you need to know the natural vibration, the natural period of vibration of your soil columns, in this case, you can use DS profile obtained from empirical correlation. So it means from SPT or even CPT. They say internal damping of soil should be measured with appropriate laboratory or field test, knowing that actually there is no reliable way or even no way to measure the damping ratio from in situ test. And if it's not the case, if you cannot make direct measurement, you have a low level of seismicity, you can use a very small damping ratio that is equal to 0.03. And finally, concerning the variation of the soil stiffness and damping versus the shear strain. So once again, he repeats that we should take into account the effect of shear strain in the value of the Gmax. And after that, he say that for local soil condition, this is a bad soil, C or G. And if you have a shallow water table, water table, and if you under certain condition of plasticity index, if you do not any data coming from a site or from a laboratory test, you can use this reduction coefficient for the value of Vs, okay? Depending on the acceleration that you have at the soil surface, so it comes from the map. We will see that from the courses on the response of the soil column, from the map, for instance, of the France and the category of soil and so on. You can have this value of acceleration ratio, and you can use this value for the degradation of the value of Vs and of Gmax. And also, if you, under certain conditions, it gives you some value for the maximum damping that you can have. So you see that there is still a difference of analysis between what we can obtain, for instance, in research, with very beautiful degradation curves and things like that, in the framework of a thesis or a research project, and what we use in practice. Because in practice there is no so many money, except a very huge program where you can have some lab series of lab tests or series of institute tests, but most of the time you do not have, and here they only give some values. So it's been here, this is an approximative way to take into account the degradation of the soil property. So now, this is all for soil dynamics, so you see very quick. Now we are going to speak about dynamics of soil and theoretical model for soils, because one of the things, when you have big projects, for instance, you have to make some estimation of the response of the soil column, and after that, but it will include soil structure interaction, of the response of the building when it is founded on a certain kind of foundation and on a certain kind of soil. And for that you need some theoretical representation of the behavior of your soil that are calibrated, and this model can use some experimental data, for instance the degradation curves, or they can use directly the response of a test, for instance a triaxial test, for a calibration, okay? And they can adjust the parameter of the model to fit correctly, for the numerical model to fit correctly what we obtain experimentally. And once you have calibrated your model, once you have calibrated your models, you are going to validate this model. So without changing the value for the different parameters, you are going to simulate on another conditions, on another lab test or a centrifuge test, so on. And is the difference between the numerical result and the experimental work is not very far. You can say that you have validated your model, okay, and in this case you can use your model to estimate, for instance, the deformation or the displacement of the building, and to see if they are admissible or not. So if we restart from the degradation curves, so I remind you these figures which represent the degradation curve of the shear modulus and the degradation curves of the damping ratio, knowing the high effect of the plasticity index on this kind of degradation curves. So the selection of the type of theoretical approach will depend on the level of the shear strain first. So if we have very small shear strain, so it means that the shear strain is equal or below the elastic limit for the shear strain. In this case, we have the behavior of the soil can be classified as a quasi-linear. So it means that it's quasi-elastic. We do not have plastic deformation. Of course, we do not have degradation, and it means that we can use a linear model, so that do not integrate the plastic deformation. If we are in the domain of a small shear strain, so it means that the shear strain is between the elastic limit and the volumetric threshold limits. In this case, the behavior is non-linear, so we start to have evolution of the damping ratio and evolution of the shear modulus value, but we have a weakly elastoplastic behavior. So you have superposition of elastic deformation and plastic deformation, but the plastic deformation are relatively small. In this case, you have no degradation, or very, very small, so it's not taken into account. And you can use what we called an equivalent linear model. Okay, I will explain later what it is. After that, you can have moderate to large shear strain. So it means your shear strain is higher than the volumetric threshold. So you start to have pore pressure if you're in undrained condition, or you start to have volumetric deformation if you are in drained condition or in saturated condition. So the behavior here is non-linear, and you have an elastoplastic behavior. So the plastic deformation cannot be neglected. So you have degradation because the shear strain is higher than the volumetric threshold shear strain, and in this case you have to use non-linear models to represent the behavior of your soil. So starting with you want me to switch on the lights for us? We are going to start with the linear behavior. So most of the time we use radiological models to have an easier understanding of the behavior. So here this is the model of the spring. So the stiffness of the spring is represented by the value of the shear modulus, and here how we are in the elastic domain, we consider the value of Gmax, so the maximum shear modulus for distortion lower than 10 to minus 5. And here the shear stress is related to the shear strength through the value of Gmax. Okay, so we can determine the value of Gmax from geophysical test. As we have seen in the Eurocode, it is recommended to use geophysical test to determine this value, and most of the time, so it's easy to have the density of the soil. Or if we do not have any money for a first approach of the problems, we can use also an empirical expression that you can find in the literature. So the value of Gmax here you can see is dependent of the void index E. So you have here some expression of the function f. This is a function of the void index. It's also dependent of the over consolidation ratio, that is the ratio between the higher stress states over the actual state of stress over the higher one. It's also a function of the atmospheric pressure and the mean effective stress. So there is several expressions in the literature, but here this is let's say the two main well-known expression. And so this is a very simple model, but very limited, because so it describe only the linear case, and as I told you, very quickly we start to have non-linearity. So as soon as we have a linear behavior, which model should we select? Because we have several options. So there is three main options. So the first one is what we call the linear equivalent models. The second one is the non-linear models, and the third one, the most complicated one, is the constitutive non-linear model. So the main difference. So the linear equivalent model, in fact, this model used the degradation curves. So it used the value of G and its evolution versus the shear strain, and the value of the damping ratio, and also its evolution versus the shear strains. So this is an iterative process. So it means that, for instance, on an earthquake, we are going to consider the average level of distortion during the earthquake, and we are going to consider the degraded value of G of the shear modulus and of the damping ratio, and we are going to make a kind of linear calculation after that, okay, by using the degradative value and by using complex shear modulus that include the value of the shear modulus and the value of the damping ratio. I will show you that later. So it's a simple model. For instance, when I say simple, is that I will show you in the next courses. There is a macro under Excel that enable you, by using this approach, to calculate the response of the soil column. Okay, so with Excel, so it's not very complicated. But there is big limitation. As one is an equivalent linear model, you cannot obtain the residual deformation, and it can be a key point when you make such interaction. Okay, you cannot also consider the volumetric deformation, and of course, in undrained condition, the pore pressure generation. So it's a very limited, but it's a first approach. So sometimes it's very easy to make some calculation like that. So it's a first approach, and we see we can have some knowledge from the analysis of this approach. After that, if we see that it's not sufficient, we can go to the non-linear models. These non-linear models are not based on the physics of the soil behavior, just like constitutive, it means what it means, constitutive non-linear model. The non-linear model, in fact, describe the strain stress path through function, through expression. And they had some additional expression or law or formulation to take into account, for instance, volumetric deformation, pore pressure generation, or when the loading path becomes more complex. So they had additional law to try to follow the stress path. Okay, but it's still limited to not so complex stress path. So for instance, for an earthquake, this is very complicated stress path. So the last steps is the constitutive nonlinear models, but we can use the other before, because this one, if you start to use this one in practice, you should have a very good knowledge, okay, of this approach, because this is a very complicated approach. Most of the time the calibration and the validation phase are not so well done, and you can say something that is completely different, but what is going to happen. So we need to be very careful with this approach. In fact, this model represents the behavior, the physics of the behavior inside the soil. So it's possible in this case to represent a lot of details, so the residual deformation, the volumetric deformation, the pore pressure generation, and yeah, you can normally represent whole, but the phase of calibration and validation are very important. Some constitutive nonlinear model, you can have, for instance, 15 parameters. So you can turn the button of 15 parameters, so you can imagine what can happen. So concerning the linear equivalence model. So in this model, so we consider, as well as I say, the loops is characterized by two parameters, the shear modulus, the second shear modulus, and the damping ratio. And for this model, the first one, elastic, it was only a spring. Here, this is an assembly in parallel of a spring and a dashpot. Okay, we see the viscosity of the material. So, with this rheological model, we linked this time the shear stress to the shear strain and the velocity of the shear strains with the point. So it's the velocity of the shear strain. And so it's also linked to the shear modulus and to the viscous part of the behavior with the coefficient of viscosity. Now, we are for the courses consider that the loading is an harmonic one, this one, but you know that earthquake can be represented by a superposition of harmonic waves, so it's linked. And here, if we consider the complex formulation of the harmonic loading, and we integrate this formulation into the equation that linked the shear stress to the shear strain and the velocity of the shear strain, we obtain this formulation, okay, versus the shear strain. And here you can see that if we replace this expression that integrate the shear modulus and the damping inside the soil, we have this kind of expression with a G stars. G stars represent all this part, and G stars is what we call the complex shear modulus. Okay, it's an easier way to represent the hysteretic behavior, because here we have finally the shear stress that is linked to the shear strain through the complex shear modulus. The only difference between the elastic representation and this representation is the stars. It includes the damping aspect. Okay, so this is a complex value. G star is a complex value, as you have the A coming from the expression of the loading. Now, if we, from this expression, if we calculate the area of the loops, we obtain this expression. So it's linked to the damping coefficient and the shear strain, but also to the angular frequency. So it means that the surface of the loop depends on the velocity at which we apply the loading. But, except for clay, but for instance for sand, this is not the case. If you make a cyclic loading on sand, if you change the velocity, the result won't change. So, to overcome these problems, what an author named Jennings said, he considered that there is an equality of the dissipated energy in the soil and in the model when this model is at the resonance. Okay? So, here if we take the expression of the soil, of the damping ratio of the soil that we have seen in another slide, knowing that I will send you the slide. You will have the slide. I got your email address on the. I will see tomorrow. We have the courses. If I do not have email address, I will ask for one email address and I will send you the slide. So we have this expression, and it's mean that we have a linked. Okay. Sorry, I do not have my. So we have this relation that is equal to this one. So we remove that. So, and we can have an expression of beta equals, knowing that this one is one value that is equal to at resonance of the system. Okay, of the logical systems. Okay, so the objective of the linear viscoelastic model is to establish a relation in the form of the shear modulus, that link the shear modulus to the distortion, that satisfy the condition of dissipation of energy and the stiffness of the soil. Okay, so there are several approaches that has been proposed by the several authors. So, and some of them have some drawback. For instance, here if you consider the soil, the exact dissipated energy by cycle is this, and the exact the shear modulus that we consider is this one. There is several models that has been proposed. This one that overestimate the shear modulus has been quickly abandoned. This second one that overestimate the damping is, I don't know exactly why, the most used. And this one that have a right representation of both parameters is not so used. So don't ask me why. I think it's very difficult when people are familiar with one expression to change. Alors, the thing is that sometimes this is not sufficient when you start to have a pore pressure built up or volumetric deformation. You cannot use the linear equivalent model, and we can easily see that. For instance, if we make a calculation with the code IRA, that is the Excel sheet that we can use to make a calculation of the response of the soil column. As this is an iterative process, he will make a first calculation by assuming some value of the shear modulus and the damping. He will make the calculation, and one of the results is the level of distortion. If the level of distortion does not correspond to the assumed value of the shear modulus and the damping ratio, is going to change this value to the couple of shear modulus and damping ratio is going to be selected from the value of the shear strength that has been obtained from the previous calculation. And this is an iterative process. But if at the end we have a calculation, so we have a result, there is a convergence of the value of the shear strength and the value of the shear modulus and the damping ratio that has been considered. So all seems okay, but the problem is that sometimes the level of distortion that you obtain, you cannot neglect the fact that you have a strain distortion higher than the volumetric threshold strain. So in this case, you have to go to nonlinear model or to constitutive nonlinear model. But we are going to start with the nonlinear one. So the nonlinear, and I will Yes, I think I will stop with this slide. I think it's almost time. Ah oui, it's time. So, if we want, we are going to stop here. So, I will start that tomorrow because we have 4 hours of courses tomorrow afternoon. So I will finish that, and we will start with the response of the soil